Hi. So today, as the first speaker, we have Alice Barbora Tumpach. She is a research director at the Wolfgang Pauli Institute, as well as the deputy head of the mathematical AI and machine learning group there. She is an expert in infinite-dimensional differential geometry, a topic she will be covering today, especially its applications to AI. So please welcome Barbora.
Thank you very much for this kind introduction. Thank you very much also for the organizer for organizing this event. I'm really very impressed by the people that are joining and the way it's organized. You have all my respect for that. Thank you. And thank you for being here this morning. So we talked about infinite dimensional geometry. That's a topic I'm working on already for years. I'm working on the theory and on the applications. So as you can see, there are two grounds that are covering my founding my research. The first one is called Barbora groups and integral persistence, and the second one, more recently, geometric linearity on groups and closure spaces. So what I will do today is following. First, I will give you a crash course on infinite dimensional geometry. Then I will focus on one notion that is important for the talk, the notion of fiber bundle and section, sections of fiber bundle, principal fiber bundles, and then if time permits, I will give you three methods to get rid of symmetries in applications. Okay, so far so good. Let's go. So why infinite dimensional geometry? First of all, it's fun. It's diverse, and it is fundamental. It is at the foundation of many different topics, many different fields. So here I have listed some of these. Geometry, of course. Think of geodesics on the sphere. The geodesic will be the shortest path between 2 points. The shortest path means that you are have a variational problem. You trying to minimize the cost function, which is the length versus the energy. So you're on the space of curves, actually, and the space of curves is infinite dimensional. So at the back of all the finite dimensional geometry, there is infinite dimensional geometry behind. Also, partial differential equation, of course, functional analysis, space of operators, spaces of acting on the Hilbert space, quantum physics, field theory. We will use some ideas of field theory. Actually, in this talk, we will see some gauge sweeping, probability statistics, and also machine learning and AI. So, why infinite dimensional geometry? As I said, it's everywhere. So here you can see some shapes deforming. So we have a path in the space of shapes. Here you go from a horse to a cat, you deform it. Perhaps you have a parameterization, perhaps you don't have. That's infinite dimensional manifold behind the manifold of shapes. You can think of manifold of human beings or the shapes of humans, okay, with links to Gaussian design, so different morphology, different shapes. You can go continuously from one shape to another. Or you can think of vector fields. Here you can see the magnetic fields on our planet. This is the field that gives you the direction of north, kind of, and it's changing with time. So if you go to the, there is a link, you will have the slides. You can click on this or go to this web page and you will see the magnetic fields changing over the last 200 years. So this is a infinite dimensional manifold in two ways. First of all, at each point you have a vector. You have infinitely many points, so you have like infinite dimensional manifold of vectors, and also it's changing in time. So you have a moving vector field. But perhaps you're more interested in shapes and different representation of shapes. So here you can see different representation of the Stanford bunny. Here I'm not interested in the bunny in itself. For my talk, this bunny is one point in an infinite dimensional manifold, the manifold of shapes. Okay, so there are two manifold. I will recall what manifold means. But think of like a shape. There are two manifold here: a finite dimensional one, two-dimensional one, or three-dimensional one. If you look at inside, and also the manifold of all shapes, which is infinite. This is the one that I'm interested in. So different representations, and of course, different ways to treat them in applications. But abstractly, for me, this is a two-dimensional manifold, and perhaps you want to change it, inform it. So you will look at two-dimensional space, the space of two dimensions. We encountered molecules in the talks yesterday. So perhaps for you, this is a graph. For me, this is also a graph, but not only. For me, there is infinite dimensional feature vector at each node, which perhaps corresponds to the level of energy of atoms. So there is a Hilbert space behind infinite dimensional vector space, and the operator acting on it. There are equation, Schrodinger equation. You look at eigenvalues. So there is, yeah, like an infinite dimensional vector, feature vector. And of course, you look at bounds between atoms. And for me, yeah, this is also an infinite dimensional phenomenon. Okay. So to make the link with the talk of yesterday, there are higher structure, a higher order structure behind, and perhaps infinite dimensional geometry can help. Because yeah, the bounds are actually a phenomenon that comes from quantum physics and infinite. Okay, so now what are the questions? Well, one research question will be, how can I fight that rotation? Yeah, the aim, of course, is to build more sustainable algorithm. And here is a very easy application. So you have shapes like these leaves, and you want to recognize them, classify them. And of course, these images are presented like this, but the algorithm of recognition should be independent of the way they are oriented in space. So you have the rotation group that is acting on each image. And yeah, sometimes people use that augmentation to allow the neural network to learn the symmetry. Of course, if you add data, you add. You need more computational power, more memory. And okay, for finite dimensional groups, that's fine. For infinite dimensional group, forget it. So here, there is an infinite dimensional group acting, and we will see it a bit later also, which is a group of parameterization. So the point of your shape are not really relevant. What is relevant is the shape itself. So what is in blue downstairs. And if you look at one of these shapes, for instance, this horse, there's infinitely many ways to represent it. So here it's a representation by parameterization, but it could be something else, some mesh, or because the points on the shape, the position of the points are not really relevant in this. So infinitely many ways to represent one of these shapes. And of course, you want to get rid of this variability. And I will show you 3 ways to do this at the end of the book. But I will mainly focus on this kind of object. So the mathematical object behind is the notion of fiber bundle and quotient space and group action. Okay, so we will do this notion. Okay, so crash course on infinite dimensional geometry. This is differential geometry, so the basic notion is the notion of manifold, which is really easy to understand. It's like all planets, meaning at each point you have an open set and a chart. So like the chart that I got to come here. Okay. Locally, every base is flat. So a manifold is like this. Locally, it's flat. And flat means that you can find an open set around each point where you can flatten it, have charts, and do computation there process. And of course, if you change charts, then everything goes well. You can go from one chart to another, a bigger chart. For instance, on one side I have the Imperial College, on the other side I have London, and you can go smoothly from one chart to the other. So there are change of charts. These are this function here. When you compose charts, when everything should be smooth. And so the basic notion behind this fundamental notion of manifold is the chain rule. The chain rule is the following: if you have three different charts, well, if something is smooth in this chart, when I say smooth, I say C infinity or CK or something. If you draw a curve here and here in this red piece here, and you look at how this curve looks like here. If it's a smooth curve here, it's also a smooth curve here. And the same in another chart. So basically this notion, you can define it on any kind of space as soon as you have the chain rule. Or that's on graphs like that. The model spaces, I will talk about it later. The model spaces that I'm using, these are in my case infinite dimensional model spaces, but for now on you can think about Rn. So this notion of manifold is based on the following definition. First, the definition of a chart, this one. The definition of an atlas, so a collection of charts. So a chart is not only the open set and the big piece of paper, but also the map that go from the open set to this one. Then a collection of charts, and also we put together all the charts that are CK equivalent to a given one. So this means that now if I want to look at more carefully in this building, I can just invent a new chart that give me more precise information of the building. And then the definition of manifold is a house of topological space with an equivalent class of atlases. So I'm not sure it's really necessary to go through the mathematical version of this. I think you can just keep the intuition. But yeah, a chart, as we said, it's a triple, an open set, map, and an open set in your modeling space, Rn or some other vector space, topological vector space. An atlas is a collection of charts, and that has CK when the change of the coordinate change, once the change of charts are of this class CK. Okay. Then equivalence of classes. If you add some charts to the atlas, and everything is still CK, and it's this equivalence class. And yeah, house off means that if you take two points on your manifold, on your object, then there are open sets that distinguish them. So you can find two disjoint open sets that separates these 2 points. And that's it. So why do we have this picture? Yeah, because I was mentioning CK. So what is K? So in the talk of yesterday, K was 0. These were topological manifolds. If you were just in the class of continuous maps, then K is 0. If you're in the class of differential functions, then it's C1. C1, you can talk about tangent spaces. C2, you can talk about curvature. And I think the big difference between these two pictures is on the left, it's less smooth than on the right. And I'm sure you can see this. So the curvature is more smoother. So it's at least C2. I mean, yeah, you can see this, right? Okay, these are the application, of course. Yeah, because reflection tells you how smooth your manifold is. Okay, so now in each field, there is a list of theorems that are the building blocks of the field. So if you're entering a new field, go to an expert and ask him, give me 5 theorems that are important in your field. So here are the 2, 3, 4, 5 theorems that are really the building blocks of infinite dimensional geometry. And you see different model spaces. So for finite dimensional manifold, the model space is Rn or Cn if you are in the complex category. For infinite dimensional manifolds, you have choice between Hilbert spaces, this behave very well, Banach spaces, pressure spaces, locally convex spaces, very weird. And these building blocks are, yes, more or less available. Perhaps you need to go to National Theorem at some point. If you are interested, you can click on the link here. Afterwards, there's a video where I explain this theorem and the proof. Yeah, so basically for Hilbert, Banach, and Fréchet, I will not define what it is because it doesn't really appear in here in this talk. You can do geometry. Okay. Of course, when you have the notion of manifold, then you can add structure, and structure can be Riemann metrics that you were told about in 2 lectures this week. Riemann structures, or which is a subclass of symplectic structure that you can encounter, for instance, in dynamical systems, which is also a subset of Poisson geometry. You can also encounter, for instance, when you have invariance. So one of the main theorem there is Noether theorem, where you have a dynamical system, but energy is preserved, some other quantity is preserved, or momentum is preserved, something like this. This is also relevant for neural networks, but I will not go into this direction. Okay, so the golden rule in infinite dimensional is the following: never believe what you have not proved yourself. So there are lots of traps, and usually I put a slide with all the traps that I encounter, and each time I add one. Perhaps for this audience, the golden rule will be never trust what you have not implemented yourself. Probably it's also a good rule. Okay, so now we go to the notion of fiber bundle. So the name comes from this kind of fibers. So you have a field and some fibers. So this is really the picture that mathematicians have in mind, right? And so go back to this image. Just want to check my time. Yeah. Here I put together all the parameterized surfaces that have the same shape. And these are my fibers. What's distinguished is one fiber to the other is the shape. And inside the fiber, the shape is the same, but the points are not at the same places. So the parameterization is different. So there is a group acting along the fibers, which is a group of parameterization of the shape. So in my language, the group of diffeomorphisms of figure S2, because these shapes are genus zero surfaces, so homeomorphic to the sphere. So there is a group acting, which is really changing just through parameterization. So here's the definition of fiber. You have a base denoted by V and a manifold M. So the manifold M is a total space of all the shape with their parameterization. And the base is the manifold of shape without parameterization. So just the blue shapes down there. And the fiber bundle is given by projection. So when you are in one of these fibers, you can just forget about the way the shape is parameterized or the shape is represented and look only on the shape of itself. So this gives you the projection downstairs. And then there is like a triviality condition in any, if you take an open neighborhood, then your fiber bundle is more or less like a direct product on space that gives you the direction of the base and the direction, the vertical direction. Examples of fiber bundles. So you had the course on Riemann geometry. So you were already exposed to this. On the left-hand side, you see the sphere and two different tangent spaces. So the tangent bundle is the manifold that you get when you glue together all the tangent spaces. So here, it's also a fiber bundle in the following sense. If you take a vector tangent to some point P, then the projection is just forget about the vector, just take P. This will project you to the sphere, here in this case. And of course, it depends on so the base point, and then you have, in this case, a two-dimensional tangent vector at one point. So this is a tangent bundle, and you can also see it on more realistic shape, like hand. Here again, you have the tip of the finger and the tangent space there. If you change the point, you will have another tangent space, and all these tangent spaces together form a fiber bundle, which is a tangent bundle. I hope this notion is intuitively clear, at least, right? You can also think about the normal bundle for shapes that are embedded in R3. So here the arrows are pointing outwards. They are normal to this central bundle. So this is also a fiber bundle. Again, if you take one of these arrow, you forget about the arrow, but just look at the points where it is. You get the projection on the base, which is fiber bundle. Okay, so now we go to more interesting stuff. The The fiber bundle I'm interested in are formed by the roof action. And the action I'm looking for instance, are shape-preserving action of finite-dimensional or infinite-dimensional roof. So I listed a few of them that you know. Translations. Translation acts on shapes just by translating them in space. And so there is a group of translation, R2, acting on shapes. And you can think of what is the orbit of one given shape. Here I took the Statue of Liberty and I translate it in space at different positions. So these are elements of the same fiber, or in other words, they are related by an element of the group. The group action allows me to go from one shape to the other. So all of these Statue of Liberty are in the same fiber, in the same orbit under the group of translations. Down here you have the group of rotations, and again, one shape allows you, if you take a rotation, to go to the other shape. So there are rotations that maps you from one shape to the other. Here again is a sample of elements of the same orbit by the group of rotation. Okay, if you want to distinguish, or if you want to speak about the orbits if you want to go back to this picture, perhaps, yes. If I'm just interested in the shapes themselves and not the way they are represented, parameterized, you can, for instance, choose a preferred parameterization or choose a preferred representant in each of these fibers. For instance, for the group of translation, I can decide that I will look at my shape centered at the origin. Say the center of mass is located at the origin. So this will distinguish one element in my orbit. Or I can decide that my curve is a parameterized curve, and I can decide that the first point will be at the origin, and that's the way I single out one representative of my orbits. For the group action given by rotations, I can do the same. I can decide that I will represent all my orbits, all these shapes in the same orbit. For instance, in such a way that the ellipse that is approximating the best my shape is along the axis of a given frame. Or I can decide that the tangent vector of the static point is horizontal. This gives me two different ways to single out one particular element in an orbit. So behind this, there is a notion that is the notion of section of fiber bundle. But let some other examples. Scales. Again, here are elements of the same orbits, the same Statue of Liberty, but scales in different ways. And again, you can choose, okay, I don't want to have all this Statue of Liberty, I just want to choose one in my orbit. Perhaps I can choose the length of this curve is equal to 1, or the enclosed area inside is equal to 1. Two different ways to single out one particular element in this orbit. These were all finite dimensional group of shape preserving transformations. I'm more interested in infinite dimensional group of symmetries. For instance, reparameterizations. So here, these are curves. They are parameterized. So this means that I have a way to go along this curve and give you exactly where the points are located. So here you may see, I don't know if you see, but there are different parameterizations of this Statue of Liberty. Here there is a arclength parameterization, so the points are equi-distributed along the curve. So perhaps you see here better. Or so this is one way to single out distinguish parameterization of this shape. There are other ways, and we will see in this talk different ways. For instance, putting the point where there is a lot of curvature. This is a way to concentrate information on where it is needed. But okay, you see that the principle is the same. The group was infinitedimensional now, but the idea is the same. You single out one element of each orbit. So the notion, oh yeah, I wanted to show this picture. Of course, the choices that we'll do, that we'll make, will influence the downstream applications. So here, the first line, you have some leaves with different shapes, different scales. The second line, we will have randomized or scaled each shape to have lex 1. So you see the proportion are changing. And the last row, we change the proportion, the scale in such a way that the enclosed area is equal to 1. Okay, so you see the difference. In here, there was no pedal, so this shape appear really bigger than the others. Usually, it's not consistent. Here, the proportions are more. Yeah, visually better, let's say. It doesn't need to be this one that is best for your application, depending. Yeah. Okay. So changing the way the fixing. So this is called gauge fixing, by the way, in gauge theory. This is exactly the same idea. You fix a gauge that allows you to treat your object modulo some group action. Yeah. So what is gauge fixing? Behind this notion of section of fiber bundle. So this is a way to lift the blue shapes to preferred shape in the fibers. So a smooth section of the fiber bundle over manifold. So the fiber bundle is M, it's the total space of this collection of shapes. And the base manifold are the blue shapes without parameterization. So a smooth section is a smooth map from the base to the manifold itself that project to the identity. So this means that if I take my blue shape, I go with my section and then project again and again on my blue shape I started with. So perhaps a better image mathematician is this one. So here, this is a fiber bundle. This is by base, so it can be a quotient space by group action. G is a group. P is my manifold here. The fibers are the orbits by this group G. For me, this group can be the group of Riemann relation, for instance, or an infinite-dimensional group. And here you see 3 different sections, section 1, section 2, section 3, which give you some submanifold in your orbital space that allows you to lift an element of the portion to the initial manifold to distinguish one element in each orbit. Is this notion clear? We have questions. It's now our turn. I think visually is quite clear, right? Hopefully. Okay, so I was talking about space of curves. It's somehow that there is a natural section for the space of curves, which is the space of arc length parameterized curves. And you learn it probably in school. If you give me a curve, I can reparameterize it by arc length. This is 2 lines of code. So it's very, very cheap. Very cheap. The mathematical behind the mathematics are much more tricky. So this means that you have a projection from the space of all curves to the space of arc-length parameterized curves. This also means that the space of arc-length parameterized curves is a submanifold, so it has also charts, tangent spaces, smooth structure. So we have a projection on this space of arc-length parameterized curves, and you have a quotient space. All curves can be, you can think of them modulo parametrization. So this gives you only the shape, and with orientation, of course, oriented curves. So this is this quotient space. Here, looking at a curve of length 1. This is my space C1. A1 is curve of length 1 parameterized by arc length. So meaning if you have a sampling of your curve with respect to this arc length parameterization, your points will be equidistributed along the curve. And what we prove with my colleague Steve Preston is that the procedure that you do when you reparameterize, a curve by arc length, is a smooth projection on the manifold of arc length parameterized curve. And you have a diffeomorphism between this space of arc length parameterized curve and this quotient space. This is in the Frechet category. So if we remember the table that I gave you, Frechet category, you can do geometry, but perhaps you need Nash model, and we need to map Nash model theorem to prove this result. But let's go for applications. So arc-length parametrization is this one. The points are equidistributed. So this is I call it the canonical parametrization because the projection, you can just automatically implement it in a computer. As I said, 2 lines of code to take a curve to a parameterized, arc-length parameterized curve. There are other canonical parameterization. I call them curvature-weighted parameterization. So at the left, this is curvature length parameterization or proportional to curvature length. So here you see there's no point on flat pieces. The points are really concentrated where there is a lot of curvature. And you can go continuously from this kind of parameterization to arc-length parameterization. So this is an example on one shape. But what is going on here is actually, if I go back to my picture here, I have a smooth family of sections. One of these is arc-length parameterization. But there's another one which is curvature weighted, just points on curvature, high curvature portion of the curve. And you can go smoothly from one kind of canonical parameterization to the other. So there's a smooth family of sections. If I look at what's going on one of these shapes, you see this. Okay, so this will be one element of my fiber, parameterized using curvature. This is the same element in my portion, but parameterized differently. So another element is the same fiber, parameterized by arc length, and you can go continuously from one to the other. So this is a continuous family of sections. Are there questions? Yes.
So in this last theorem on the previous slide,
Yeah.
Is this for all smooth curves or did you choose?
Yeah. So the Frechet structures comes from the smoothness. Yes.
But sometimes some chooses some degree of differentiability.
Yes. So then you are in the balance setting.
I see.
It's sometimes easier, sometimes not. Yes. Yeah. So if you're on CK, you can do this theorem. Yeah, but you will lose one degree. It's not so clear because there is a derivative here, and if start with CK, actually the group of diffeomorphism CK will not make it. No, because you lose one derivative. You really need C infinity here. actually to make sense of the manifold structure of the group. Infinity, yeah. Yes?
Okay, so does this theorem also hold when you take just a manifold instead of an interval? Like first the interval in manifold, can I
Yeah.
do this?
If your manifold is a fiber manifold, yes. So by definition, so I'm not sure I get your question, but
Like the path space of the manifold.
the
Like I'm
ah
misunderstanding it. Like if I take C1 of M, that's like paths of M.
yes, yes,
And can I, does this theorem also work by?
yes, it should.
And the second thing is, do you think this is like homotopy equivalence as well? Like this,
Of course, of course. Why? Of course it is, because you change just the parameterization. You don't change the shape. So if your curve go around the hole, it will still go around the hole after you have parameterized by r length. The change, the shape doesn't change.
you might compute the homology of the path space or something,
Yes.
but it's still.
Yeah. Okay. So this should be invariant by parameterization. This is a topological invariant, right? So it really only depends on the shape of the curve, not the way you put your points around it. And yeah. So this is typically the kind of thing where everything that you compute should be invariant by parameterization. Yeah. Yeah, please.
I have another question, which is, I think we did something similar, but for discrete groups.
Oh, yeah.
For discrete,
Discrete groups, yes.
then when we did, this thing, it was called fundamental domain projection,
Yeah,
like using, like specific representative.
yeah, exactly. That's exactly the same thing.
Exactly, and one.
Well, in my case, the fibers are also smooth manifold, but in your case, they are discrete.
Yes, they become discrete ones.
Yes,
And one problem.
with the same structure. Yeah,
Exactly, and one problem we faced there was like this thing creates discontinuities sometimes.
Yeah.
And actually, the group we faced this problem with this was not discrete; it was actually continuous. So when you look at the sections, are you guaranteed that they are always continuous, or
yeah.
the sections are not discrete, but then
So in the definition, I'm not sure I put smooth in the definitional section. You can talk about non-smooth sections. But for this talk, my sections are smooth. Yeah, but indeed.
in this theorem,
Yeah.
it tells us about smooth sections.
Yes.
So they definitely continuous then.
Yeah, sure. Yes. I don't know if smooth. In this theorem, everything is smooth. Yes. Yeah, and to go back to your question about it doesn't depend if the group is discrete or not. Sometimes you don't have a globally defined smooth section.
In this case, where
In this case, we have Hartling's packet transfer. This defines your globally defined smooth section. Yes.
because like the way you define the section is that you some sort of like pick a representative in each class separately, and then sometimes
Psyche smoothly. Yes.
it becomes smooth.
Yeah. So behind I use the differential structure on the base, which is a Gaussian space. So smooth in this sense for the differential structure that I have on base, and the differential structure on the top space, smooth between these two. Yeah, this is why there's the homomorphic here written. Yeah. Other questions? Yes, so this is really what I want you to take back home. a section is choosing a representative in your equivalent class. And you can, some cases, you can do it smoothly, at least locally, perhaps not globally. Perhaps at some point you will need to have a jump. Yeah. Yeah. Okay, let's go on. I don't know how I do with my time. Yeah, I was talking about address parameterization, other kind of canonical parameterization, weighted by curvature. Perhaps it's good to recall what a curvature is. So here's a picture. When you go along the curve and you look at how the tangent vectors is changing its orientation, this rate of change will give you the curvature. For instance, around the glasses of this carton, around the glasses of the carton here, the curvature is 1 over the radius of this blue disc here. It's a change of rate of orientation of the diameter. How did I use this to represent my curve? Well, I integrated the absolute value of the curvature along the curve, and this gives you the left plot here. So this zero, I think the starting point was somewhere up here. You go around and you compute what the curvature is. And at some point you reach the mustache, which is the point where the curvature is at its maximum, just after this minimum. I didn't mention it, but the curvature is timed here. You know, you can go in one direction or the other, and you keep the sign. I mean, you record the sign. So here, this point is very curved, and this gives you a lot of curvature. If you integrate, this gives you a slot, high elevation, and there are more flat pieces, which probably are here. So if you integrate this curvature on the curve, you get a map and take the absolute value of the curvature. So I'm sure that this map is strictly increasing because I integrate something which is positive. And this gives me a diffeomorphism, a way to reparameterize. This gives me a map from 0, 1 to 0, 1, because my time to go around is, I think, parameterize my curve by 0, 1, so I go around after my parameters reach 1. And if I just rescale by dividing by the total integral of the curvature, I'm also going from 0, 1 to 0, 1. So this gives me a diffeomorphism, a strictly increasing map, and I can revert it and reparameterize my curve with respect to curvature. And this placed my sample points on the position where the curvature is the highest, and there's no points on flat pieces. Oh, this is another kind of reparameterization. Just I want to say something more here. Here I just integrated the absolute value of the curvature, but I can put some lengths in this formula, and this gives me a family, so a constant plus absolute value of the curvature, a positive constant plus the absolute value of the curvature. This will give me a strictly increasing map. A strictly increasing map will give me a diffeomorphism, or another way to resemble my curve. And this is how I constructed my family of sections that I showed you here. So on the left, that's the curvature reparameterization, and between, you can go continuously to RS. Here, another perhaps more pertinent parameterization of curves. This one I call clock parameterization, because each hour you know where you are. So on the left, you have some parameterization, and you see that after, I think, every 60 points, I change the color. So here are my first 60 points and 60 points after and so on. So you see that the angles that are created here are not equal. And the clock parameterization will do this. It will give you an equal angle. So every 60 points here, you have the same angle. This is why I call it clock parameterization. This is also a canonical parameterization of curves. So this means that automatically you can implement this. It will do the job for you. It's not curve by, you don't do it by hand, curve by curve. You just implement an algorithm. Again, there is a function that you can use for that. How does it look like for more tricky shapes? Well, if you have this property that every 60 points you form the same angle, well, sometimes you don't have enough points to, or less points to create your shape. So here, the 60 points, you can see them from where you are, I suppose. Yeah, so depending on the shape, it may be a good idea or not. Oh, yeah. So this picture is just to tell you that the choices that you make for the representative of the orbit that you are considering have really impact on downstream analysis. So on the left, I represent in 2D I think there are 75 leaves from 15 different classes. So on the left is before any normalization. On the right, I have normalized a bunch of groups. So translation is taking care of rotation, scaling, prioritization, and you see that the data set, it looks completely differently. It's almost clustered already. I didn't do any neural network yet. This is for free. You just normalize. You just choose one representative that is perhaps better for your application. And you can also optimize your sections to find the best section that's achieves the biggest separation of classes. So this is what I did here, just for this simple example of curves. But you can imagine what it can give you in more tricky applications. Okay, so this is the method, really. In your algorithm, think about it. What are the groups? What are the symmetries? How did I normalize my data sets? Did I make some choices? Perhaps these choices are not the best. Perhaps I can optimize about these choices. So I listed the groups, scaling, rotation, translation, parameterization. There are two more groups that I use here. So here in this, perhaps I can do. In this example, the data set is a data set of curves, like this one. So I normalized translation, all the curves were centered by central mass at 0. I normalized scaling, all the curves were length 1. I normalized the rotation, so all the curves are such that, yeah, they are vertical. I normalized parameterization. I used, for this example, I used clock parameterization with, I think, 4 subsections. So every pi over 2, we know where the point is. And so there are 2 more groups. What are these? What do you think? What should be? Yeah, I see this. This means orientation, perhaps? Yeah, I can flip my leaf, that is true. But in this data set, the leaf, you know, there is a more, the front of the leaf is pointing towards us. So this is not, this is already taken into account. Fine. What else? 2 more groups. Remember, to do this, I needed a computer. To implement my curve in the computer, I just recorded a sequence of points. And then the picture that you see is just linear interpolation between this sequence of points. Yeah.
Doesn't it in general depend on how you record it, like you said? Because when you record it, you kind of automatically take care of some things like the flipping. I mean, you could do it in a very poor way, and for example, have like permutation variance, and you mix up the points, and then you have to like sort them by some like positives. So can you answer this question in general even? It really depends on the data set, right?
In order to be able to plot this shape, I have an ordered set of points because I know which point is connected to the next. I cannot flip the points around, otherwise I will lose this information. And this is crucial. This is an ordered set of points. Okay.
So it's the starting point that you have to.
Starting points, yes. This is actually S1 symmetry on the parameter space. So there is a rotation that gives is simply where do we start around this contour, right? Exactly. So here I choose the point which has a higher vertical component as the starting point, the tip of the leaf. Okay, this is one of these two symmetries. Another one. Starting point was normalized in. And again, this is really crucial because to plot the next here, to plot this, I use, so this is I computed some distances on this leaf. Between two leaves, I computed the distances. Very basic one, just L2 distance, sum of square root of sum of squares between the points. So meaning the position of the points are crucial. So if I start, so here if all the leaves start at the same point at the tip, then the distance will be lower than if you start randomly, right? Okay, there is still one symmetry. Yeah, just think about it. You will probably, before the end of the talk, you will find it. I have 2 minutes, perhaps. Oh. Or how much? A bit more. Let's see. Yeah, so this one for curves. Do we have the same kind of things for surfaces in R3? So do we have a canonical parameterization, like something that will take the role of arc-length parameterization? Well, yes or no, depending. So for shapes, so like this hand, so genus 0 normal, genus 0 surfaces in R3. There is a theorem, it's called uniformization theorem, that tells you that you can parameterize a shape like this to normal using the two sphere. There is a parameterization from the two sphere to this hand that preserves actually the angles on the tangent spaces. To this, if you look at this tangent space at the tip of this finger, you can make sense of what is a relation of 90 degrees. This actually defines you a complex structure on this tangent space, and this complex structure moves smoothly when you change your point, your tangent space. So this kind of object in mathematics are called Riemann surfaces. And the uniformization theorem tells you this. If you have a complex surface genus 0, you can always parameterize it by the sphere, and there are different ways to do it, but if you fix 3 points, there is a canonical way. So this would be the equivalent of arc length. However, to implement is much more tricky. So there are algorithms based on signal packing. I don't know if you heard about this, that do this, but it's computationally very heavy. So perhaps it's better to change your point of view and not use section in this case. There's no, the sections are not so easy to treat as for curves. And the reason is on the curve, you get an ordered set of points. On the surface, there's no order, and that's the main difference. Okay, I'm almost finished. I just want to give you some ideas of how to get rid of symmetries. So I mentioned the notion of fiber bundles. Taking a section will normalize your data set. You will get rid of the symmetries in this way. So this would be the point 2. This is what we did in this talk. We choose different sections. If you choose a section, you get rid of the invariance by the group. Another way is to impose equivariance and work on the quotient space. So meaning you work with the space of orbits, and you make your algorithms equivariant, so rotation equivariance, and that's another way. And the third way would be use gauge invariance framework. So perhaps 1 or 2 slides about this. So you may need to measure distances between shapes or between classes of objects when you wrote the action of a group. So the gauge invariant framework is following. There is one direction you don't care about. This is the direction of the fibers here. Suppose you are just interested in the shapes themselves, the blue shapes, but not the way your shapes are presented or represented. So you can decompose your tangent space into 2 subspaces, the direction of the fiber, and something which will give you the horizontal direction. And here is my decomposition. Here is the cat, and the green arrows are the infinitedimensional deformation of the cat. So vector field on the cat. So pointing in the direction of the deformation. You can split it into here. Red one is tangent to the cat. So this is the direction of the fiber. This will just change the position of the points on the cats without changing the shape, because the vector has tangents. You just move the points along the surface. And here there is a component which is normal in the cats, so really pointing in the normal direction. So this will give you the horizontal direction. So mathematically, what we are doing here, we put a connection on our fiber bundle. So a way to split the tangent space to the vertical direction and some horizontal direction. The horizontal direction is here. Vector fields that points in the normal direction on the cat, and this is the vertical direction. So now, if you want some measure of dissimilarity between shapes that is invariant by the group action, you can just kill the vertical direction. Put no post here, and this is what gauge invariant means. So you can put like a Riemannian structure upstairs, but degenerate in the direction of the fiber. So you put no cost in the direction of the fiber. The only cost will be deformation of the shape and not the parameterization. In this way, you get rid of this infinite dimensional group of symmetries, because then the algorithms that you get are completely independent on the way your shapes are represented. And you can choose the representation during minimization algorithm between if you want to for instance, computer geometry between two shapes, then you can organize on the fly. It will not change anything. Okay, that's perhaps the most, yeah. I will end with one question. When do we have the whole is not equal to the sum of its parts? So in the context of a fiber bundle, so there was a question yesterday of this higher order structure that you can put on graphs. And if you just don't do it, you will not get the same results. The higher structure will give you the way graphs neighborhood sense, gives you the neighborhoods. So here my answer. When there is a topological non-trivial fiber bundle somewhere. Can think about it. That's a missing symmetry. My curves were oriented. I knew that I go down the curve in a counterclockwise way. And of course, it's half of my curves were counterclockwise. The other clockwise, it will completely change my distances, right? So what's your left, what's your right here? Apparently, the orientation in this part of the world is different from the orientation that I have. So this is really crucial. So yeah, mine is this one. Okay, I think I will stop here. Thank you for your attention.